Hello and welcome to this talk on machine learning at the edge, part of the AWS Innovate online conference, Machine Learning and AI edition. My name is Kapil Pendse, and today we are going to talk about implementing machine learning on IoT devices at the edge of the network. We are going to look at some real use cases from our customers and then dive deep to understand how the AWS Greengrass service enables these use cases. So let's get started. Why do we need machine learning at the edge? For many applications, for example, medical equipment or heavy machinery in remote locations, it is impossible to use cloud-based services to perform machine learning-based predictions. Even if they have tons of sensors and capture tons of data, there are good reasons why they cannot use cloud-based machine learning services. And that's a problem that's not going to go away. And the reason for this is the law of physics, latency and last-mile connectivity. Latency of sending data packets to the cloud and getting a response back can be unacceptable for scenarios that involve timely, automated decision-making. For example, crash avoidance and medical alerts, or equipment that is operating in remote environments, for example, mining sites, aircrafts that are in the sky, and ships at sea. Some decision-making, such as high-value safety-critical processes, must continue to operate autonomously even when internet connection is not available. AWS Greengrass provides tools for communication among cooperative devices that are interconnected over local networks, and it provides the capability to execute application code on these remote devices, enabling them to operate autonomously. Secondly, there is the law of economics. Cost of bandwidth is not falling as fast as the cost of storage and compute. AWS Greengrass provides tools for locally aggregating and filtering data, making it easy to act on lower value data locally, and upload only the high value data and aggregated data to the cloud for analytics and storage. The third set of challenges is compliance and privacy. For legal or compliance reasons and concerns around privacy, some industries prefer to store or duplicate data locally. For example, hospitals may be required to keep all records locally, even if they are also duplicated in the cloud. Some governments impose data sovereignty restrictions on where the data may be stored. We announced AWS Greengrass in reInvent 2016, and we have been astonished with the breadth of use cases that our customers and partners are bringing to us across industries. Industrial gateways from manufacturing and logistics, consumer gateways and consumer devices, connected automotive vehicles, connected wireless infrastructure, energy, agriculture, insurance, medical, mining, almost any industry you can think of. And many of these use cases involve machine learning. AWS Greengrass is an edge-based software that allows our customers to securely connect their assets, gather data, and take intelligent actions locally even when the internet connectivity is not available. It enables our customers to run machine learning applications at the edge. Let's take a look at how some of our customers are using AWS Greengrass. Yanmar is a manufacturer of agricultural equipment, climate control systems, and aqua farming systems. When actively managing plant growth at greenhouses, one of Yanmar's challenges is administering the right amount of water and environmental support, including fans and air conditioners. Plants require different climate conditions and water quantity at different stages of growth. To monitor stages of plant growth, Yanmar uses multiple cameras in each greenhouse to take pictures of the plants which are then processed by machine learning algorithms on AWS Greengrass to recognize growth stages. This knowledge is then used to control the water supply and the climate control systems. By processing images from cameras at the edge, Yanmar minimizes the cost of 3G data usage. In this way, Yanmar is able to implement a cost-efficient, smart greenhouse solution with image recognition. Nokia is another customer of AWS who saw a need to analyze video streams at the edge and send processed, filtered data to the remote centers only when anomalies were detected. To solve this problem, Nokia deployed AWS Greengrass on their Nokia multi-access edge computing platform. As the cost of bandwidth is expensive, especially in remote locations like oil rigs, this has allowed Nokia to optimize the amount of data that is sent to the cloud. Now let's take a closer look at AWS Greengrass, which seamlessly extends AWS to the devices so that they can act locally on the data that they generate while still using the cloud for management, analytics, and durable storage. Local actions and local triggers enable a local ensemble of IoT devices to coordinate and operate autonomously. Data and state sync capability allows AWS Greengrass devices to synchronize their data and their state with the cloud whenever internet connectivity becomes available. We have brought the security model of the AWS IoT cloud service to the edge of the network by enabling AWS Greengrass to identify, authenticate, and communicate with other local devices securely. Over-the-air updates capability allows you to remotely update not only the data or state or AWS Lambda functions running on your devices, but also the AWS Greengrass package itself. OPC UA is a very common protocol used in industrial IoT. We have implemented a protocol adapter for OPC UA to enable interaction between AWS Greengrass and your existing IoT devices that use OPC UA protocol. The local resource access feature makes it possible for your application code running on AWS Greengrass devices to take advantage of resources like GPUs, cameras, and the various sensors and actuators that might be available on the devices locally. And finally, the powerful feature called ML Inference or machine learning inference. It's a mechanism for you to train machine learning models in the cloud and deploy them to run on AWS Greengrass devices at the edge to process data and take actions locally. Now, you might ask, what can you do with machine learning at the edge? It's really up to your imagination. AWS Greengrass Machine Learning Inference enables several use cases. I'd like to highlight just a few of them. Think about agricultural companies. During harvest season, they could apply machine learning to quickly sort different type and quality of produce at the farm where it is being harvested instead of having to transport it back to the processing facility and sorting it there. In industrial environments, you could apply machine learning in manufacturing. For example, you can use machine learning together with video cameras to determine the quality of manufactured goods and decide whether to pack the goods for shipment or to discard low-quality goods. So, how do you make this system intelligent? If you were to do machine learning today, you would start with building and training a model in the cloud, which is a compute-intensive job. For most of the applications, you will also run the inference and predictions in the cloud. Largely, much of machine learning you see today is done through the cloud. But as we saw in our case studies, you can't always do that. There are challenges associated with cost and latency of data transfer. So, We've taken a different approach to solve this problem using AWS Greengrass and machine learning. The first part, the building and training of machine learning models, which is a compute-intensive job, you'd still do this in the cloud as you have been doing. However, you deploy the trained machine learning model on a Greengrass device at the edge. Then, whether that device is connected to the internet or not, the device can run inference on top of the data on the device itself, and it can take actions locally. AWS Greengrass ML Inference relies on a deeper feature of AWS Greengrass, which is now also available to all developers. It's called Local Resource Access. Local Resource Access lets you extend the common programming model of AWS Greengrass. That is, the AWS Lambda functions that you deploy on AWS Greengrass devices, and lets them interact with the underlying capabilities of the AWS Greengrass host device. For example, a GPU, sensors, actuators, and so on. In this way, the AWS Lambda functions that are written in the cloud and deployed to AWS Greengrass devices can start to interact with the devices and the physical environment around them. Now I'm going to show you a demo of machine learning inference on AWS Greengrass. If you have ever done scuba diving or snorkeling, then you might have noticed how the underwater natural beauty is being polluted by artificial debris, plastic bags, discarded beverage cans, fishing nets, and so on. There are a number of seabed cleanup efforts happening around the world. What if we could build a machine learning model that can detect the presence of litter by analyzing images from underwater cameras? Such a model could be used to process the photos and videos from underwater drones or underwater cameras carried by divers to create a map that identifies places with high density of underwater litter. Such maps could potentially aid the seabed cleanup efforts. Now, I don't have an underwater drone, but I was able to get some images from such drones. And with that, I was able to train a model that can distinguish between marine life and litter with a fair degree of accuracy. Admittedly, my model was trained using a very small data set of less than 300 images, and therefore leaves a lot of room for improvement. But it will serve the purpose of this demo. I have used Amazon SageMaker to train this model. During the demo, we will deploy this model to AWS Greengrass and perform ML inference on AWS Greengrass using this model. So for this demo, the first thing that we need is a machine learning model which can distinguish between marine life and litter. In order to train such a model, I have downloaded images of underwater cameras from this website of Jamstack e-library of deep sea images. I have downloaded roughly 300 images as my training dataset, and I have used Amazon SageMaker to train a model using the notebook instance feature of Amazon SageMaker. So let me show you what that looks like. If I click on this link, it should open the notebook instance, which I have already opened here. And here you can see my Jupyter notebooks that are running on this notebook instance. So let me go ahead and open the notebook for you. Okay, so as you can see that I have written my code for the training of the ML model in this notebook. I have used the transfer learning capability of Amazon SageMaker to use a pre-trained model that is trained on the ImageNet dataset and retrain it to differentiate between marine life and litter using my dataset. So let me skip down to the portion where I am downloading my own data set. So as you can see, my data set is placed in an S3 bucket, and I download that data set over here using AWS CLI commands. And once that is downloaded, over here I'm using Amazon SageMaker SDK to configure a training job and set some hyperparameters. And this is where I execute that training job. Once the training job is complete, I use another API of the SageMaker library to deploy this trained model to an endpoint that is hosted by Amazon SageMaker. So I have already executed the notebook until this point. So we already have a machine learning model that is trained. Let me show you that. So this is the model that has already been trained, and I am already hosting it at this endpoint. And in the notebook, I am going to make API calls to this hosted endpoint to run inference against some sample images. So let me go ahead and show you a few sample images. Let's just see if the trained model really works according to our expectation. So I have an S3 bucket where I have placed some sample images that I want to test. One of them is loaded here, as you can see. I'm going to modify this and show you a few more images. Let's start with some images of litter first. So when I execute this block, we get a new image, and that gets rendered here. And then over here, that same image is sent to the hosted endpoint of the model. And we should see a result here. So now I'm going to execute the image, and there we go. We can see that according to this model, the prediction is that this image is litter, and with a probability of 77%. Let's try some more images. Here is another image of something that should not be on the ocean bed, the seabed. And once again, the model says, yes, this is litter. Now let me show you some images of marine life. We want to make sure that the model detects marine life as marine life rather than litter. So let's try this image here. So here is a fish, and let's see what the model thinks. There we go. The model thinks, yes, it is a marine life form. It is fairly confident of this fact. Let me try another image. Another type of fish. Once again, we get the desired result. And here is not a fish, but a different type of marine life form. And once again, we have fairly good result. Now, of course, we are using images that are fairly simple. As I mentioned earlier, I have trained this model with a fairly small data set of 300 odd images. So there is plenty of room for improvement of this model in terms of accuracy and its ability to deal with more complex images than this. But for the purpose of this demo, this model will do. So we have this model hosted at this endpoint. Now we want to deploy this model to an AWS Greengrass device. So like I said earlier, I don't really have a underwater drone with me. And for the ease of demo, I have deployed AWS Greengrass on an EC2 instance. So in order to deploy my model to that Greengrass running on EC2 instance, I have downloaded this model from here, which is a compressed file, as you can see, and I have uploaded it into an S3 bucket. So let me show you my Greengrass configuration. So here you can see this is the configuration of my Greengrass group. This Greengrass group consists of a single Greengrass core device, a machine learning model that I have defined right here under resources, and I am pointing this configuration to download my model from an S3 bucket right here. So the model sits in S3, and I have made a selection from my bucket where I have uploaded it, and this is the one. Okay, so also I have a Lambda function that is running on the Greengrass device, because the model alone doesn't do anything. We need to write some business logic in a Lambda function which makes use of this model that gets deployed to the Greengrass device. So now let me show you how do I configure this. So in the same Greengrass group, I have also configured a Lambda function, and there are certain parameters that I have configured along with this Lambda function. For example, the memory that is available to this function and some environment variables, including the path where this model will be accessible for this Lambda function. The same path is also configured as the local path of the machine learning resource that we have just defined in the Greengrass group configuration. There we go. That is the local path. So now the model is deployed together with the Lambda function to my Greengrass device, and my Lambda function can access this machine learning model locally. In this way, my Greengrass can continue to operate even when there is no internet connectivity available. So now let's see what is inside this Lambda function. So this is my Lambda function code, and I will give you a quick walkthrough of what is happening in here. Since this is running on an EC2 instance, I don't really have a physical camera that is connected to my EC2 instance. So I have placed some sample images in an S3 bucket. I have 8 different images, and I have programmed my Lambda function to randomly pick one at a time from these 8, download them to this Greengrass device, and then analyze them using the local machine learning model. I have also configured some simulated location coordinates because I wanted to visualize the results of this demo on a map. As I said at the beginning of this demo, what if we could generate a map of where exactly there is higher density of litter? That would help the cleanup efforts. So that is why I am simulating some location coordinates, and let me show you how all of this is used. So this is a long-running Lambda function. Long-running Lambda functions is a feature of AWS Greengrass that allows this Lambda function to keep running endlessly. So the first thing that we do is we load the machine learning model. Remember, I showed you the environment variable, which points to the location of the machine learning model on the Greengrass device. So that environment variable is being accessed right here. And in this class, I am using MXNet libraries to load that model. Once the model gets loaded in memory, now I can make API calls to this model, local API calls, to run predictions. So in this loop, it's a very simple loop the first thing it does is picks a file name randomly from my array, downloads that file from S3 to the Greengrass device, and then it sends that file to the MXNet library to run inference against my model. The results come back as category and probability. So my code checks whether the category that is predicted is litter, and if it is litter, then I simulate some location coordinates for this particular image, and then I push the results to an AWS IoT topic. If the results are not litter, I simply print a log message saying what was the result and what is the probability. So now let's see all of this in action. Switching back to the AWS console. This is the S3 bucket where I have the sample images, and they are already being downloaded randomly by my Lambda function because I have already deployed all of this to my Greengrass running on EC2. So let me go ahead and show you the logs that are coming through. So this is CloudWatch, my log group for my Lambda function on Greengrass. And as you can see in the logs, the function is downloading images at random. And then if the result is marine life, it simply prints out the probability or the confidence level. If the result is litter, it prints that message out, and it also simulates the location coordinates for that image and publishes the message to AWS IoT topic. So let's see what is being received at that topic, the topic being submarine-greengrass/results. So let me go to test in AWS IoT console. Submarine-results. Submarine-greengrass /results, and I subscribe to this topic in my console, and let's wait for a few seconds for the results to start showing up. The Lambda function itself is going in a loop, and every 5 seconds it pulls an image randomly, runs an inference, and then if the inference is found to be litter, it publishes the message to the IoT topic, and then it goes to sleep for 5 seconds. There we go. So we have a result here. Image 04.png has been found to be litter, and there are some simulated coordinates for that. So let's see if this is really litter. I have this image downloaded on my computer as well so that I can show you quickly. This is 04.png, and as you can see, it is a fishing net that is captured in this image, certainly not a marine life form. Another image 01.png is being reported as litter. Definitely it is a beverage can, a soda can. So it appears that the machine learning model deployed on the AWS Greengrass is working as expected, and the results are coming through to the AWS IoT console. Now what can we do with this data? So I have configured an AWS IoT rule to act on this data and transfer this data using Amazon Canisius Firehose to an Amazon S3 bucket. And in this rule configuration, I am extracting only the payload value. So instead of the entire message that was coming through to the IoT topic, I'm extracting only the payload value string. And that is basically a CSV string, something like this. This is what gets stored to my selected S3 bucket, which is configured in this rule. So this is the Amazon Canisius fire hose configuration. So the IoT rule forwards the data to Amazon Canisius fire hose, and from there it gets sent to the Amazon S3 bucket, which is configured in Amazon Canisius fire hose. And I have configured this fire hose to deliver the raw data at this particular folder within my bucket. So let me show you what is actually landing inside my bucket. You can see that Canisius fire hose has partitioned the incoming data by timestamp, and if I drill down, we can see that the raw files are generated right here. So now I want to visualize all of this data, and to do that I have used Amazon Athena. Amazon Athena is a serverless query service which allows you to write simple SQL statements to query the data that resides in your Amazon S3 bucket. So in this query, I am pulling out the data that is sitting in my bucket, and I'm extracting only the latitude and longitude columns. And that is working well. And in order to visualize all of this on a geospatial map, I have used Amazon QuickSight, a BI service, and I have created a dashboard which shows a map, and on this map I can see the location of all the places where litter was found. Of course, these are simulated locations nearby the island of Tioman, and a map of this nature can be used by people who are doing efforts for cleaning up the seabed. So that's a wrap for this demo and for this session. Thank you for watching, and I hope you found that interesting. You can visit the demo arena and watch how machine learning is used in real-life applications. You can also get your questions answered by AWS experts. And for more information about machine learning on AWS, please visit aws.amazon.com/machine-learning. To gain more confidence and hands-on experience with AWS, you can access the digital training built by AWS experts. You can also attend instructor-led classes that are delivered by qualified AWS instructors and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. AWS certifications validate your technical expertise with AWS. If you wish to get certified, practice exams are available to help you prepare for the certification exams. Thanks again for attending, and we really appreciate your feedback so that we can better understand the topics and services you would like to know more about. So please do take the time to fill out our survey and let us know what you think. Thank you.